Very good. Good morning. So we will start the lecture. But before I do, I want to ask you people to discuss when would be a good time to have a mid-semester exam. We will need a 3-hour slot. And if we are generally discouraged from having doing things during the weekend, but that might be the most relaxed way of doing this. So one possibility is to do this in the weekend of 30th, 31st October. So please discuss this among yourself. Can I ask the two representatives to discuss this among yourself and find a 3-hour slot, preferably the weekend of 30th, 31st, and see if you can. I believe the others are also trying to fix mid-semester exams. One thing that has been suggested is do it during the week, but that might be a bit rushed. So I'm not saying that I will lecture every day of the next week, but nonetheless, it might be better to do it over the weekend, except the Saturday morning is already taken. So maybe Saturday evening or Sunday morning or Sunday evening, if that suits you people. So can I ask the two representatives to take the lead on this?
Yes, sir. But I think like Aditi herself would not be available that weekend.
Who will not be, sorry?
The other representative, Aditi. I don't.
Okay. She has something else to do that weekend. So yes. Already, so if, no, it is not just a matter of one person. If generally there is an issue, then we will have to go and fix this during class hours, so there is, I think people are discussing how to do it during the week. That is also okay for me. Okay.
Okay,
sir, excuse me.
Tell you.
Sir, on Friday we have a long slot. Like in the morning we have lectures 11:45. That's it.
Yeah. So that is the problem. No? So so if we start, if you have a lecture at, I mean, if I have to start the exam at 9, then we would not get 3 hours, right? So unless we do this Friday evening.
Yes, sir. I'll ask and let you know.
Yeah. Okay. So very good. So let me start the class. So we have discussed how linear maps from Rn to Rm are the same as M cross N matrices. Meaning there is a natural bijection which preserves addition of matrices on the one hand and addition of linear maps on the other. And in fact, this also extends to compositions. If I consider a further vector space RL on the left, in which case I would have M cross N matrices and N cross L matrices, and the multiplication would give you an M cross L matrix, okay, which would be a linear map from L to M. So this bijection I've been talking about, and if you have read my notes and looked at the exercises, you will have some idea. Though I believe that this would mean that you have to go past the little sign that says you are here. I hope you don't take that sign too seriously. Anyway, now today, what I'm going to do is to go back to more or less your high school days and remind you what you did to solve systems of linear equations and how that can be interpreted in terms of matrix operations. And this is a really important thing to do because this will lead us on to a certain formalism called reduction of a matrix to row echelon form, which is a very, very useful technique, both for theoretical and practical reasons. Okay, so today's lecture will start with very familiar things from high school. So that way you should be somewhat comfortable. Let's start. Okay. So the topic we are heading towards, this topic called row reduction. But we will start with very basic things with linear equations and matrices. Okay, consider two linear equations for two unknowns and two nodes. Okay. So what do I mean by that? So there are two variables. Let me just write down a11 v1 plus a12 v2 is equal to v1 hat a21 v1 plus a22 v2 is equal to v2 hat. So in high school, you would have studied, you would have been asked to solve this. What does that mean? Given v1, v2, which are real numbers, everything in sight is, so these are all real numbers. Find, if possible, v1, v2 such that the two equations hold. And if more than one solution exists, find a way to list all solutions. So these v1, v2 are called, if you find a v1, v2, that's called a solution. And so solution may or may not exist. And in high school, I hope you have studied methods of systematically seeing if solutions exist. If they exist, if the solution is unique. If not, list all solutions. Okay, so this is something familiar to you. So how would you do it? Well, so what would you do? You will see if a11 and a21 are both 0. Well, I would say nothing to do. You're clear what to do. Okay, I will not elaborate on this. You know what to do. So can suppose at least one of them is non-zero. And by relabeling, can assume a11 is non-zero. Okay, so I'm saying that if both of these guys are 0, then I'm not saying what you would do because that is clear to you. So, and then so at least one of them is non-zero, and I am assuming that this one is non-zero. Okay. So what would you do? You would multiply the first equation by so if A11 is non-zero, multiply the first equation by A22 by A11, and subtract the resulting equation, subtract from the second to get A11V1 plus A12V2 equal to V1 hat, and A11 A22 minus A12 A21 over A11 V2 equal to V2 hat minus A21 V1. I'm just copying from my notes because this is not something I can do without that easily. And you go on like this. Okay. So this is a so this is so finally we would get, if A11 A22 minus A21 A12 is non-zero, we get V1 V2 by is given in terms of formulae, something on the right with this A11 A22 minus A21 A12 in the denominator, and similarly something on the right with the same thing on the denominator. Okay, now this is something that you are very familiar with, but now I'm going to redo exactly the same thing in terms of matrices. So you start with A1, exactly the same equation that we started with, but except now I write it in matrix form. Okay, so now rather than your what is given to you, so is a 2 by 2 matrix A given a column vector of length 2, which I call V hat given, and so you are asked to find if a vector V with coordinates V1 to exists. That solves the above equation. So let me call this just V. Solves the above. Now this is a matrix equation. If solution is unique, if not, list all solutions, or find a way to parameterize all solutions. Okay. So now the point is, all the steps that we did can be interpreted as multiplication on the left by certain very specific kinds of matrices. So I'm not going to do that working out in front of you, but let me just, you should think of it schematically. So the first step, yeah. So the first step, for example, so let's go back to this first step that we did. Multiply the first equation by A21 over A11 and subtract the resulting equation from the second. Okay. So remember, that's what we did here. Okay. So what did we do? We took this equation. We did not do anything to it, anything to this equation itself, because that continues here. That equation itself, we have not done anything. But the second equation has changed. How did it change? I take the second equation and subtract another equation from it, which then what is the other equation that I get? So let us see that. So what does that mean? So this means this step is, I have the second. So let me write down the second equation. This is the second equation. And if I multiply the first by A22 by A11, I get A22 V1 plus A12.
It should be A21, A11, I think.
Just here, you mean?
Multiply the equation by A21 by A11. At least that's what you did in the notes.
Okay, yeah. Here.
So also if you see, you've subtracted A21 by A11 on the right.
Yeah, is this correct? Now, if you see, have I corrected it now?
Yes, that's right.
Yeah. So from here I get sorry, this should be V1. Sorry. So I had, this is the second, so let me be careful. This is the second equation, which I have rewritten, and this is the first into A21 by A11. That is this equation. This is the second equation. And I've subtracted this one from this one to get this. So my point is, all that thing that I said in words can be done in terms of matrices as follows. Take this equation A11, A12, A21, A22, V1, V2 is equal to V1 hat, V2 hat. Take this matrix equation and multiply on the left by this matrix 1, 0, minus A21, A11, 1. So multiply both sides by this matrix. Okay. So then that would, if I implement that, I would get, and then whatever I get is the same as what you would have gotten here. So okay, and the whole sequence of operations that I have, that you would have done to solve the equation would be gotten by a whole series of matrices, matrix multiplication on the left, which I will again write down for you. So repeat. So put this equation, matrix equation, here in between the curly brackets, and there are 4 matrices that I will write down. They are in the notes. And then multiply again on the left by 1, 0, 0, A1, 1. And now I am introducing a notation, det A, which we have not, strictly speaking, defined. And then one more equation, one more matrix, which again is in the notes. Okay, so so this whole process of solving the equation by various operations is got by multiplying on the left by matrices of a very specific kind, and then seeing what happens. Now, so what is this det A? For this 2 by 2 matrix, it's just A11, A22 minus A21, A11, which is we've already encountered here. So this was the condition. So this step, so the step star, let me call this step star. Star can be done only if det A, which is this expression, definition, is non-zero. But so what to do if that is non-zero is, so just as we, so think of this like a flow chart. So this is like a flow chart. The flow chart will go like this. If A1, so start with the equation. Start if A, I've forgotten how flowcharts work. Is A11 R, A11 and A21 both 0. If yes, well, I've said you know what to do. If no, at least one of them is non-zero, then you do this, relabel if necessary. So A11 is non-zero. Then you ask, then you do the first step, this multiplication by this guy. Left multiplication by this matrix. Then you ask, is dit A non-zero? If yes, continue. And that is the whole sequence of matrices that I have here. If no, if no, then I will again say, you know what to do. We don't quite know, but you know, I mean, there are things to do. So the specific algorithm is not so important at the moment. What I want you to focus is that there is an algorithm, and so one of the ingredients in the algorithm is whether dit A is 0 or not, but this is not really the important one, because this becomes relevant because you have an n by n, you have a square matrix. You have as many unknowns as we have variables, which is the case because you have equivalently you are working with square matrices. So the determinant being 0 or not is an important condition. But in general, that will not come into play. What will come into play is that this algorithm proceeds by multiplying a matrix equation on the left by matrices of very specific kinds. Okay, so let me write down. By the way, this is all quite carefully explained in the notes. So don't worry if the details are not clear in the lecture. In the lecture, my job is to give you an overview of what's going on. Okay, so what should you learn from the lecture so far? So there are 2 points. The algorithm proceeds. Point number 1. Proceeds by multiplying on the left by matrices of specific kinds. So unfortunately, with 2 by 2 matrices, it is not immediately visible what are the kinds of matrices that we are using on the left. As when I describe the procedure in general, I will do this more carefully. But the more important, or equally important, is that the actual vectors, known and unknown, so remember the known is what I call V1 hat, V2 hat, and unknown is what is V1, V2, don't play a role in the computations. So why all the operations are acting on this matrix and making it simpler. So the actual vectors, as I said, are spectators. So they are spectators. So I'm going to now step back and describe something much more general. Okay, so we'll start. So what I'm going to do now was motivated by this elementary example from your high school. Namely, you have to solve a system of linear equations in 2 unknowns and 2 knowns, and you were taught to do a series of operations with these equations, and I have reinterpreted them in matrix terms. And what happens in matrix terms is that there are matrices of very specific shapes that you choose, which operate on the equation by multiplication on the left. And this is something that we are now going to kind of generalize. Okay, so now comes, question.
So these vectors v1, v2, and v1 cap, v2 cap are not necessary to be vector of R. Like they could be vector of R square or R2 or R3 also. Like
no, they are, in this case, they are, what do you mean vectors over R2? They are these are vectors in R2. These are column vectors of length 2 with coordinates which are real numbers. So these are so we are working with real numbers everywhere. So I don't know what you mean vectors over R2, R3. No,
so v1, like v1 itself is a vector.
No, v1 is not a vector. This is so when you see, just think, have you studied systems of linear equations in high school?
Yes, sir.
So you have studied two equations and two unknowns, right?
Yes, sir.
So that is all I'm doing, and that is what I started with. So yeah. So Shakti, so don't make this more difficult than it's necessary. So the starting point was just something that you did in school. Two linear equations for two unknowns and two knowns. What are the knowns here? The knowns are what is given to you, that's on the right hand side. Two real numbers, v1 hat and v2 hat. And you also given the four coefficients, a11, a12, a21, and a22. So this, a specific example could be a specific example. If I give values to this, so let me use this space, 4x plus 3y equal to 3, 2x plus y equal to 1. Okay, this is a specific. So I'm just taking an example like this. Here the unknowns are x and y. So the vector, this is an example of such an equation. So I'm just, so whatever we have done is what you would do. So this is an example. Okay, so if you had an equation, so supposing I had this equation like this, what would I do? You would divide the first equation by 2. So you get 2x by 3 over 2y is equal to 3 over 2. Then I would subtract that from the second equation. I would get something and proceed. No? Is that clear?
Yes, sir. So yeah. XY are the components of the vector, like the column vector XY.
X and Y are the real numbers.
Yeah. So in general, they could be anything else, like if we consider them to be vectors also.
No. We are trying to do something. I'm just taking something that you did in high school as a starting point to introduce this procedure called row reduction. So don't make this more difficult than it should be.
Yeah. Okay, sir.
Okay. Yeah. I mean, you understand, no?
Yes.
This is something. So given this equation, you were taught how to solve it using some specific series of steps, right? You do this, then you do this, then if the determinant is not 0, then you do this, blah, blah, blah. If it is, then something else. So hopefully you know how to follow a series of steps to solve an equation like this. All I'm doing is doing that and then interpreting that in terms of matrices systematically. Every step that you did in school, I'm saying corresponds to a certain matrix operation, multiplication by a suitable matrix. That is all I'm doing. And this is all this is just to introduce you to the next step, which generalizes this. So don't make this more complicated than it should be. Because then if you get confused at this stage, then it really makes my purpose is to introduce you gently to the next step. So you should not get confused at this step. Is this clear?
Yes, sir. Yes, sir. Yeah.
No, I want to be careful. See, trying to make something easy, I should not end up making it difficult. That is why I'm a bit anxious. Okay, so
it's fine, sir. Fine.
Yeah. Okay.
Thank you.
Okay. Yeah. No, it's okay. No, it's thanks for it. So you see, don't get very intimidated. Don't get frightened by my flowchart. Flowchart is something that you just I'm just trying to sort of tell you in a slightly formal way that if whenever you encounter a systematic way of doing something in mathematics, that corresponds to what in programming we call a flowchart. At least in the days when I studied programming, I started by writing a flowchart. Okay, for example, long division is it says, look at what you look, do this, do that, if this, then that. So that can be made into a flowchart. Okay, so I'm just saying that your whatever method you were taught to solve linear equations can be made into a flowchart. That's the first thing. And then I'm saying that in fact that method corresponds to writing your system of linear equations as a matrix equation. So if you have m equations in n variables, that can be written. So rather than thinking of this as m equations, you think of it as one equation, except that now it's an equation between some equations involving matrices. That everything that you did while trying to solve linear systems of linear equations can be reinterpreted in terms of matrix multiplication by choosing suitable matrices to do your jobs for you. Choose a matrix, multiply your matrix equation, both sides of your matrix equation by the same matrix from the left. Then choose another matrix and again multiply. So, a series of, Shakti, do you, and in fact, everybody else, do you understand? See, not the details, but what I was trying to say here. So what do I mean by this, for example? What does this mean? It is supposed to help you visualize something. So I have this matrix equation. I choose this matrix, and what this means is make this matrix do something to this equation. And what can a matrix do to an equation? Well, it can multiply both sides by, this matrix can be used to multiply both sides. Then I'd get another equation. And so that is the first step here. Then choose this matrix to multiply so this will give you some equation. Then choose this matrix to multiply that equation. Then choose another matrix to multiply that equation. So all the steps that you did can be reinterpreted as going from one matrix equation to another by choosing different matrices and then multiplying on the left. By multiplying on the left, I mean I have an equation with matrices. Take this matrix and multiply both sides by instead of just like you would multiply one equation involving real numbers by the same real number on both sides. An equation involving matrices can be transformed into another equation involving matrices by multiplying by a matrix on the left. That's all I'm doing. Okay, that is what is meant by everything that's written here. I can stop. I can, if anybody is lost here, I can say this again in more explicit ways. Do you want me to do it? If anybody, you can even tell me in chat.
Also, sir, could you explain like why are we multiplying with this particular matrix with the?
No. I cannot. I cannot explain why we are. I'm just saying whatever you did in solving the equations is the same as this. So that is something you have to check. So asking me to explain why we are doing this, choosing this matrices to multiply, that's like asking me to explain why you did something at the linear equation level.
Yeah, yes, sir. Yeah, fine.
Okay, Akash Yadav. So could you just repeat what you said just now? So
I was basically asking the determinant of A is A11, A22 minus A21, A12, right?
That is the definition. I should, at some point we will spend time talking about determinants, but at the moment I don't want to. But you know determinants, no? 2 by 2 matrices.
So I know. I was just saying that the expression that in the
yeah, I have already said that. I have said that.
No.
You mean
sir.
My expression is wrong?
Yes, sir. And you have written A21, A11.
Yeah. Thank you.
Yeah.
I keep making such mistakes. Thank you. A21, A12. Thank you. Yeah. Okay. So can I go on now? Okay, so now let me make the basic definitions and results in the row echelon reduction. Okay, so the first thing, so we are going to, so we are going to, so now I'm going to spend some time with some definition. It will not be clear to you for some time why I'm making these definitions. So you'll just have to sort of accept that this is, so think of this as a preliminary to going forward. So the definitions I'm going to make are of a class of n by n matrix. So these are, first of all, so let me call, so the topic is elementary matrices. So these are some special kinds of square matrices. Okay, so I'm going to, so I hope you remember what square matrices are. These are matrices where the number of columns and the number of rows are equal. Okay, so I'm going to take among all square matrices, I'm going to single out, I'm going to tell you there is a special class of matrices, and we have not yet defined what is special, and they are important in what is going to follow. So, and I have to first of all tell you what they are. I'm just given them a name. They are called elementary matrices. Now I am going to describe them to you. Okay. Okay. So before I do that, I want to so this is what we are going to do. But before we, so this is already some preliminary, but we are going to do some preliminary, little preliminary to this big preliminary. Okay. So let me give some, go before that and do that. So for the space of M cross N matrices, we have a basis of matrices what is the notation? Just 1 second. I want to make sure I choose the same basis. Eij where I runs from 1 to M, N runs from 1 to N as follows. Okay, so I will give you the definition in a minute, but so let me create some space for myself. Okay. I'm going to, well, I can tell you what the basis is, but I'm asking you, so can you tell me, give me a basis? So the M cross N matrices are of this kind. I have M rows and N columns. So, and I have real numbers here. So what is a natural basis for this space of matrices? I've even given you a
The
hint.
ijth element being 1 and rest of them being 0.
Very good. Yeah. Who was this?
Nilabjo.
Yeah. Is this clear to everyone? So if I choose an I, which is in the row range 1 to M, and choose a J, which is in the column range, so Eij will have so this is the ith place, and this is the jth place, and it will have 1 here and 0 everywhere. So this is the matrix Eij, and as so definition. So Eij is the M cross N matrix, which has 1 in the intersection of the ith row and the jth column, and 0 everywhere else. And as I runs over 1 to M and J runs over 1 to N, you get a basis for M cross N. Is this clear to everyone? I think this is even an exercise. So for example, if I take the 2 by 2 matrix A11, A12, A21, A22, this is equal to A11, E11, A12 E12 plus A21 E21 plus A22 E22. So this looks like a crazy equation, but which are the matrices here? These guys are the, so let me give them colors. These are all matrices. And these are all scalars. And this is an equation in the vector space of 2 by 2 matrices. So I have one, so this is, so in equivalently, I'm writing A11 E11 plus A12 E12 plus A21 E21 plus A22 E22. So this is an equation in the vector space of 2 by 2 matrices, which tells you that this 2 by 2 matrix, this vector in the space of 2 by 2 matrices, is got by taking this vector, multiplying it by this scalar, adding it to this vector multiplied by this scalar, and adding that to this vector multiplied by this scalar, and adding that to this vector multiplied by this scalar. And any 2 by 2 matrix can be written uniquely like this linear combination. So the four matrices E11, E21, E22, E12 form a basis for the space of 2 by 2 matrices. And you can do this for matrices of arbitrary shape, and that is what we just did before. And we are going to define elementary matrices in terms of these basis vectors. And there are three kinds of elementary matrices. One, choose I not equal to j and a scalar a, and consider the identity m cross n. So fix m. So we consider m cross m elementary matrices. So as I said, elementary matrices are special kinds of square matrices. So let me fix the size of the square matrix I'm considering. So that that means fixing m and looking at m cross m matrices. So the first type of elementary matrix look like this. I take the identity matrix of size m cross m, take a scalar a, and multiply this Eij, where I is not equal to j. So this is the, remember, this is a basis vector in m cross m. So this is a matrix, m cross m matrix with all entries 0 except at the intersection of the ith row and the jth column. Okay. So what does this look like? 1, 1, 1. Then at the ith row and the jth jth column, I put A, and everywhere else 0. So, so 1 along the diagonal and A at the intersection of the ith row and the jth column, and 0 everywhere else. So this is the elementary matrix of the first kind. Elementary matrices of the second kind. Choose I not equal to j, and once you do that, then you have 1, 1, 0, 0, 1, 1, 1, and 0 everywhere else. So this happens at the ith and the jth row, ith column, jth column. So we have 1, 1, 1 everywhere except at the I. So this is the intersection of the ith row and the ith column. This is the intersection of the jth row and the jth column. There you have 0, but you put a 1 here and a 1 here. So this is the elementary matrices of the second kind. And finally, you have elementary matrices of the third kind, where you have.
Sir, could you just say about
1 second.
the above structure?
Let me just,
Okay.
yeah. 1, 1, 1, C, 1, 1, 0, 0, C is non-zero. So this is third kind is a diagonal matrix. All entries are 0 except along the diagonal, and all the diagonal entries are 0 except 1. And that exceptional diagonal entry is a non-zero real number. Very good. So now I have listed the 3 kinds of elementary matrices, and now I will answer your question.
Sir, could you explain the second structure once again? The second element.
Yeah. Yeah. Can I take a little break? My throat is, yeah. So anyway, so before I take the break, so the second guy has all entries are 0. Okay. So in other words, so okay, let me explain a special case of the second special case. Is 0, 1, 0, 0, 0, 1, 0, 0, 0, 0, 0, 0, 1, 0, 0, 0, 0, 0, 0, 1, blah, 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 all the way down. Okay. So here I and j are equal to 1 and 2. Sorry, 2 and 2. I is 2 and j is 2. Okay. So what happens is that the at the no, I is 1, j is 1. I'm sorry. I is 1, j is 2. So what you do is you in this block you just okay. Just see what happens. So take okay. So see what this matrix does to the vectors. Okay. So if this matrix, let me call this matrix E, acting on the basis vector EK will have the following action equal to EK if K is not equal to I or J. And if, yeah, just EK if K is not equal to I or J, E acting on EI is EJ, and E acting on EJ equal to EI. So I was going to do the following. I gave you the shape of the 3 kinds of elementary matrices, And I was going to say what these elementary matrices do to column vectors. So I'm going to do that for elementary matrices of the first kind and third kind also. But since you asked about elementary matrices of the second kind, the description of the elementary matrix you may not see so clearly from the picture, but maybe this will help you. What the elementary matrix does to the normal basis vectors of the column vectors, the kth vector ek it leaves alone unless k is equal to I or j, and the basis vectors ei and ej are flipped. Does this help?
Yes, sir.
Okay, so let me now take a break. My throat is